Hello everyone. So today what we're going to do is we're going to work another nodal analysis example. And along the way we're going to introduce the concept of a supernode. So I'm going to go ahead and just jump right into our example and outline the steps for doing nodal analysis with including the concept of a supernode. And I will explain the definition of all of that. So let's just jump right into our circuit example. Let's suppose you have a current source here, and then a voltage source, and then a resistor, and another resistor, and then a current source, and a voltage source, another resistor. Oh, and then I meant to draw a resistor here. There we go. So we have R1, R3, R2, and R4. I'll call this one I1, I2, this VS2, and this VS1. So let's go ahead and do nodal analysis to solve this problem. So step one is label all nodes. Okay, so we can label this as node 1. This can be node 2. Node 3. Node 4, and I'll call this node 5. And then our next step, step 2, label the reference node. Or I should say label a reference node, since you can pick any one of the nodes as your reference node. So I'm just going to go ahead and select node 1 as my reference node. So then the next step, you're normally used to just then applying KCL, right, to each node. But in this case, the next step, let's see if I can, maybe I'll start at the bottom here. So the next step step 3 is circle all supernodes that do not contain the reference or ground node. So now you're probably wondering, what the heck is a supernode? Basically, anytime you are working a nodal analysis problem and you notice that there are voltage sources present in the circuit, then you're going to need to use this whole concept of a supernode if you want to solve the equation using nodal analysis. So the definition of a supernode is this. We're going to define it as an interconnection of voltage sources. It can be just one source, so I'll put that in parentheses. And nodes, and containing no resistors. That are grouped together and treated as a single node with KCl being applied. So essentially the whole idea behind a supernode is that you can, so we're used to applying KCl to just a single node, right? The sum of the currents into a node is equal to 0. But it turns out you can kind of expand that whole idea and say that if you have, for example, just a blob of circuits and you don't know what's inside of it, but then you have, let's say you have wires that are poking out and you know what the currents are going in and out of the blob. You know that based on conservation of electric charge or mass, that what's going in has to eventually come out. And so basically the sum of all the currents going into this mysterious blob is going to be equal to 0. So it turns out we can kind of basically do that with like the whole idea of a supernode. We basically group together an interconnection of nodes and voltage sources, no resistors, just nodes and voltage sources, and um, we treat them as a single node, summing all the currents going into it by applying KCl. So here's an example of a supernode in our circuit. So here we have two voltage sources here, right? And a supernode is basically it's a grouping of an interconnection of nodes and voltage sources. So we could actually group these two voltage sources and call this whole thing a supernode. And essentially what we can do is we can apply KCl to this supernode by summing all the currents going into the supernode. So this current I1, the current through R2, the current through R3, this I2 current, current through R4, and R1 here. You can sum all those and it should be equal to 0. Now, the reason that we employ this whole idea of a supernode when we're doing this nodal analysis is that if we went ahead and just did KCl at our individual nodes here, you would run into a problem with the final step when you're trying to express the currents in terms of your nodal voltages. So for example, if you wanted to apply KCl to this node here, you'd have to sum, okay, this current going in, this current going in, which you could do that, right? But then what's the current going through this voltage source? We know how to express it with a resistor, right? That would just be V3 minus V2 over R2. That would be the current through this resistor. But then how do we express current going through a voltage source? So that's the conundrum that we run into. And so that's why then we introduce this whole concept of a supernode where we basically group up our voltage sources so that then we can just apply KCL to the whole thing and we don't even have to worry about what's inside. So, this third step here, we circled all supernodes that do not contain the reference node. So we defined our reference node here, and you can see that none of these nodes here are connected to our reference node. If we had defined our reference node over here, which we could, then that would mean that the supernode did contain the reference node. And in which case, we don't need to write a KCL equation for that. Not because we can't, I mean you could, but it turns out with the way the math works out that you actually wouldn't need to apply a KCL equation to the supernode. You would only need to apply KCL to all your other nodes, and that would give you enough information to solve the circuit. But in this case, with the way that we've written our ground, here we want to circle it, and it's important that we identify it. So now that we've identified that, our next step is to, step 4 here, is apply KCL to all nodes and circled supernodes. Okay, so let's go ahead and do that with our circuit here. So now let's go ahead and do step 4, which is applying KCL to our nodes and supernodes. Let's start with supernode 1. So we have supernode 1 here, and we're going to sum all the currents going into the supernode and set that equal to 0. So here we have I1, and I1 is flowing into supernode 1. So we can say I1 plus the current coming in, let's say from R1 here, we can call that IR1, and we can define it in this direction. So plus IR1 plus the current from R4 here, so I'll call that IR4 plus this current here, but the current is going out, right? So it'll actually be, to count the current going into the supernode, it'll be plus minus I2. And then we have plus this current through R3. So we'll define that as IR3 plus the current coming in on R2, IR2 and that is all equal to 0. So we've applied our KCL equation to this supernode here, and then we want to examine these other nodes to see if we need to apply KCL. Well, with node 2, there's nothing else connected, so we don't need to apply KCL there. And the same thing goes for node 4. So we can then, it's node 3, it's the only other node that we need to apply KCL to. So then we do node 3. So again, sum of all the currents going into the node equals 0. So here we have I2 going into the node, right? So I2 plus the current going into node 3 here, which would be, because of the way this is oriented, it would be minus IR3. So plus minus IR3 plus this current IR2, but it's oriented outward and we want the current going into the node, so it would be plus minus IR3. Or IR2, excuse me. And that's all equal to 0. Then the next step that we want to do in our nodal analysis is apply Ohm's law to each KCL equation. So what we want to do is we want to express all of these currents using Ohm's law. So IR1 is equal to, so this is our reference point, right? So IR1 is equal to minus V5 over R1 because of the way we have this oriented. It would just be V5 divided by R1 if it was in this direction. So that's equal to minus V5 over R1. And then IR2, let's see what that will be. IR2 would be V3 minus V2 divided by R2. And then we have IR3. IR3 is going to be equal to V3 minus V5 divided by R3. And then finally we have IR4. And because of the way this is oriented, it's going to be minus V4 divided by I4. So now we've expressed all of our currents, except for, of course, these known source currents, I1 and I2. We've expressed all these currents in terms of our nodal voltages and resistances. But we need a few more equations, actually, in order to solve our circuit here. So the next step, step 6, when you're working with these circuits is express voltage source values in terms of the nodal voltages. So if you look at the voltage sources we have here, this voltage here, Vs1, has to be equal to the difference in voltage between the two nodes that it's connected to, right? Because the voltage is difference in potential, and we are given the voltage right there. It's Vs1. So we can write that Vs1 is equal to V2 minus V5. And in a similar manner, we can write that V5 minus V4 is equal to Vs2. So here we have, so we've got we've got, so we've got four unknowns, right? We're not including, so this V1 is just 0 volts, right? So we've got 4 nodal voltages, which is 4 unknowns. And notice that we have 4 equations. We've got our 2 KCL equations, and then we have our 2 source voltage equations. So that's basically, we've got 4 equations, 4 unknowns. It's a matter of then you can plug and chug and put this into matrix form and then solve for the voltage, the nodal voltages. And so that's how we can solve this circuit. So the steps I've outlined will pretty much work for any sort of nodal analysis circuit, whether you have voltage sources or not. And in the next video, I'm going to talk about how you could do this analysis differently if you place the ground node at a different node, and it all works out, and so it really doesn't matter. But there are different ways of approaching it. So I will discuss that in the next video. Thanks for watching, and I'll see you next time. Hello everybody, thanks for watching. If you found this content helpful, would you please consider liking and subscribing to the channel? That will help other people find it. And if you won't do it for me, will you do it for my cat, Muon? Named after my favorite subatomic particle, by the way. So, she will be very, very upset if you do not like and subscribe. So please, don't disappoint. How could you say no to this cuteness?